And now we're going to actually model data using some sort of polynomial. Okay, now it says the chart shows how much milk Wisconsin dairy farms produced in these years. What linear model best fits the data? So it says specifically what linear model, which means we're going to find what? Yeah, it's going to be a line. Then it says use the model to estimate milk production in 2000. We've done this before. You've been doing this since Algebra 1, so it shouldn't be that big of a deal. But then down below, like after we do that, it says now generate a quadratic model for that data. Okay, now that's where this section comes into play, and then we're going to compare the two models and talk about what we see. So, where's the data? Yeah, it's on the little milk things here. How are we going to handle the 1955, 1980, 2005? Yeah, we are going to eventually do that. We're going to plug it into our calculator. Can I say 1, 2, and 3 here? No, because we're talking about years. That would be like year 1, year 2, year 3. That's not the case. We have 1955, 1980, and 2005. We could make this 0, which would make this 25, and then this one 50. We have that option. We could stick with 1955, 1980, and 2000. We could say that 1900 is 0, and in that case then this would be 55, this would be 80, and this would be 105. I like to go with the option that's going to give me the smallest possible numbers as my answer. But when I do that, I have to remember that I've changed the numbers that were given to me into these numbers here. So when I go to plug in 2000, I'll have to remember that. Now, once I make my model, will 2000 be interpolation or extrapolation? Did we talk about that? We didn't? Okay. It's actually interpolation. Think of like extraterrestrial. Extraterrestrial means not of this world, outside of this world. Extrapolation means, oh, it's on the next page. Okay, so extrapolation means outside of the data. Extra, the prefix extra means like outside of. The prefix inter means within. So interpolation is within the data. Extrapolation is outside the data. Okay, so we want to take these 3 data points that they give us and plug them into our calculators using the spreadsheet so that we can create a scatter plot. So let's go ahead and do that. Okay, so here's the scatter plot with the linear model on it. It gives us the equation y equals 0.128x plus 17.4. We're going to write that down. Obviously, I can't show what the calculator is showing me on my homework, so I'm going to write the equation down here. It's y equals 0.128x plus what? 17.4. So there's my linear model. It says use the model to estimate the milk production in 2000. So what am I going to do? Why 45? Right. This is 1955. 2000 is over here, but we started at year 0. So that means in our model we're going to have to plug in 45. So y equals 0.128 times 45 plus 17.4. And then you enter all that into your calculator, and what do we get? 23.16 billion pounds of milk. So before we go on to the next part, let's talk about this answer. What do you notice? Our answer. Right, we were given 1980, we're given 2005, and the answer that we got is 23.16, higher than either of these. Is that okay? What am I doing? 2. There we go. Explain it on the graph. Here's 45 right here. If I go up, there's my y value that I just found, which is higher than these two guys here. So is that okay? Yes, it is okay. Why is that okay? Exactly. We use a linear model. The linear model predicts, or actually finds the interpolation, which we'll talk about in a little bit, of the model that we used, which is between our data, and the model came up with an answer that is higher than what we would have expected to see probably. Because probably as time goes on, what's going on with production rate? It's increasing. But we would expect it to increase from here to here, but never go higher than this number, right? That's kind of like logically what you guys are seeing. So this is the right answer, but I'm going to ask you things like, does that answer make sense? Is the answer right or wrong? Why does the answer make sense, or why does the answer not make sense? That's the point of this section. So the answer is right because our model says so. The answer doesn't really make sense because we would expect it to increase from here to here like it did, but land somewhere between here and here. But because we were asked to make a linear model, we saw something a little bit different happen. So let's use the data to also generate a quadratic model. So let's go back to the calculator, and we can just use the same data. We don't have to change anything. We can just ask it to give us a quadratic. So go back to Analyze and Regression Quadratic, and it will give us the parabola that fits that best. Now notice that I was only given 3 ordered pairs, and I have a parabola, so we knew, or we should know, that that parabola is going to go exactly through all 3 points that were given. So I want to write this equation down. It's going to take me a minute to remember all of it, 0.00432x squared. And then what was the, it was a negative, wasn't it? And then what was the rest? Plus point what? Okay. Use the data to also generate a quadratic model. We did. Compare the fit of each model. So compared to the other model, what would you say? The quadratic one fits it perfectly based on the 3 data points that were given. But what? Yeah, it's showing over here that all of a sudden now our milk production is going to decrease. Is that logically going to happen? Or suddenly, when we get to year 63, the cow is starting to decrease their milk production for some reason. They're going on strike. They're dying off. We just don't care about milk anymore. We just drink Coke. Is that logical? No. It's logical that the graph should continue to rise. So to answer the question, which model is best? We said compare the fit of each model. The quadratic is definitely a better fit. But which model is best? The linear is best. Why is the linear the best? Because it represents the situation better. It's more realistic. Within the data, maybe the quadratic is better than the linear. But outside of the data, that quadratic starts to show that we have a decrease in milk production, which doesn't make sense to us logically. So that's why the quadratic model is not as good. What if I was to give you another ordered pair? Another ordered pair would allow me to create a cubic polynomial perfectly. Would that be best? So let's say I gave you, this is addition to 25 years each time. Let's say I gave you 75 years from 1955, whatever that year is. Let's say we're in the future sometime. And I wind up with like 28. So now my graph has this, 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 and then this. Does that look like a cubic function might fit that? Yeah, a cubic function would fit it. First of all, because there's only 4 points. Second, because I specifically gave you something that would fit it. And third, answer the question. Would a cubic model be best in this case?
No.
Why not?
Yeah. No. Because it would show that the production slowed down and then sped back up.
Okay, so within this data right here, a cubic model might be best. That's right. So then, like a year later, we're going to be taking off here. I don't want to use the word exponentially, but I think you guys know what I mean by that, because it's not really an exponential takeoff that we're doing here. But this thing is going to go up for forever, really, really fast. Whereas the line would kind of hit, kind of miss all of my data points. Do you see the difference already? Right here, this is going like sky high, to where by the time we get to like 2100, the year 2100, there's more cows on Earth than there are like ants on Earth. And that's probably not going to work out so well, right? So probably my answer here would probably be more like no, outside of the data. But within the data, so would a cubic model be best? Sure, yes, within the data. But outside of the data, the linear model is going to be best, because the linear model shows a slower rate of growth, and that's kind of what we would expect from this situation. So no, outside the data. Lots of words. Go ahead and read them. Okay, a couple of important things on this little screen of words. It says data that's generated by a law of physics. So like data generated by gravity. Or some sort of geometric formula, like when you did your project. And we had the one part of the project that was the length of the square and the area of the square. You generated that data using geometry, using a formula. So that data was perfectly accurate. You'll have a mathematical model that fits the data and yields accurate predictions, always, because it was generated by a formula or some other law of physics. With other data, like sales records, or the length of your foot based on, compared to your height, stuff like that. Stuff where you're collecting data not generated by some sort of formula. Then you can approximate the data only within or close to the domain over which it was generated, which means if I have a set of data, I can generate a model for that set of data, and I can talk about that set of data with that model. I can talk about anything within the extreme points of that data. I can talk about that model sort of outside of that data. So let's say I come up with a model that looks like this. I can talk about anything from here to here accurately. I can talk about stuff slightly outside on either side of that model. But beyond that, typically the model starts to fail pretty drastically. And that's what this is trying to say. As long as it's data that's collected, not generated by some sort of formula, this is about the extent of your model. You need more data outside of your model in order to be able to talk about stuff over here. Anything within the model is okay though. So using a model to predict a y value outside of the domain of a data set is called extrapolation. And like the prefix extra means outside of. Estimating within the domain is called interpolation. This is interpolation here. This is extrapolation. This is extrapolation. Anything beyond that is extrapolation, and I'd be pretty hesitant to call it certain. Interpolation usually yields reliable estimates. Extrapolation becomes less reliable as you move farther away from the data. So if I'm in here, my extrapolation might be okay. If I'm picking a value over here, it might still be okay. Might not, but it might be. Anything beyond that and you're really risking causing yourself lots of problems. Okay, the table shows average annual consumption of cheese per person in the U.S. for selected years from 1910 to 2001. Pounds of cheese per person. 30 pounds of cheese in 2001. That's a lot of cheese. But you got a whole year to eat it. That's only like 2.5 pounds per month. That's only a pound a week. But that's how much the average person eats. A pound a week. Uh-huh. Well, there's 16 ounces in a pound, 7 days in a week. So a little over 2 ounces a day. It's not very much. What do you think about it? Okay, so for selected years from 1910 to 2001, model the data with a cubic function, it says. Use the model to estimate cheese consumption for those 3 particular years. Which estimates do you have a high confidence in? Which estimates for 1980, 2000, and 2012 would we have a high confidence in? Why 1980 and 2000? They're within the data. So the model that we generate, this cubic model that we generate, is going to be a very close match for the data that we have, within the data that we have. Outside of that data, like 2012, way outside our data, not as close of a match. But we can still find the estimate. Okay? All right, so we want to make a spreadsheet with this. We can do it on our calculator. Do I want to start at 1910? What do I want to start with? You could start with 10. I like 0, personally. So if I start with 1910 at 0, then that makes 1940 what? And then 1970 is, it's 60. 75 would be, 95 would be, and then 2001? 91. So just keep that in mind. You want to do that before you start entering your data in. Let's go ahead and do that. So here's my scatter plot, and then one more time I'm going to analyze a regression. And this time they specifically said cubic, so I put a cubic model in there, and there's the graph. How well does it fit? Seems like it fits really well. It might not be exactly right on because of the fact that we have got a lot of data points there, but it's pretty close. So we're going to need to write that equation down, and I'm not going to be able to remember it. So we have y equals 0.000092 x to the third minus 0.006812 x squared plus 0.146689. And I need to move my equation over because I can't see anymore. I don't know how you guys are, but I couldn't see the rest. X plus 4.04261. Nice and long, lots of numbers, but that's the model. So it said model the data with the cubic function. Here's my answer right here. Use the model to estimate cheese consumption for 1980, 2000, and 2012. Now what am I going to do? Plug it all in. Type it into your calculator, press enter, and you will get each one. So for 1980 and 2000 and 2012, what am I entering in for 1980? 70 and 2000? 90 and 2012? 102. Good. So one option you have is to graph the equation, which I did over here. You can go back to your scatter plot to get the scale for the axes that you need. My x-axis scale is from 0 to 90. My y-axis scale is from 0 to, I think I did 40. Just so that I see the same graph. There it is. And now I can show the table and figure out what the answer is for any of those. So for 1980, we said was going to be 70 years down the road, so I had my table start at year 70. And I get 12.488. If I want to find out 2000, we said that would be year, what, 90? So I can just scroll down until I get to 90. 29.1354. And then the last one, 2012, would be what? 102? So then I scroll down to 102. 45.764. It takes a little bit longer to set it up, but then you can find any number of points that you want. And if it's a long way away from one point to the next, then you can just change your table settings to start the table over at the next one. So let's get those answers written down here. Remind me what they are. I have 45.76 for 2012. And what's 1980? 488, right? 12.49. Okay. And 2000 was what? Okay. And that's what? Pounds of cheese. So in 2012, we are consuming 45.76 pounds of cheese. So in 2015, how much is that? Well, that's easy to answer because I have in my calculator, all I got to do is go down to 105, and we're consuming over 50 pounds of cheese per year. So you can use the calculator to help you, even though we're sitting with this equation right here. All I did was enter it into the calculator's graph, and then I changed the scale to match my scatter plot. The scatter plot gives you the scale. It's very easy. So, do we have a high confidence in that 2012? I really hope not, because if we're eating 45 pounds of cheese, we're kind of in bad, well, actually I probably am, but we're probably in bad shape if we're eating that much cheese. All cheese. No. All right, so high confidence in 1980? Yeah. If you look, 1980 falls between 10 and 25 here, and we got 12 point something, so that makes sense. For 2000, we have 29.14. 2000 is just shy of this 30 sitting right here, and we have 29.14, so pretty close. 2012, on a number line, that's way outside of our data. So that is definitely an extrapolation, which is far away from my data. If this was like 2002, I'd have a pretty high confidence still. 2003, yeah, probably still. But once we get to like 2005, 2006, it's starting to like falling apart. 2012, bad. This is low confidence here. All right, using the data above, repeat using a linear model, and then we'll discuss the results of that. So I'm going to go back to the calculator and make a linear model. Well, I need to go back to my scatter plot. And then you analyze regression linear this time. So now we have this equation, 0.269867x minus 1.22. Yeah, it says repeat using a linear model, using the data above. So let me write this equation down. It was 26 what? 987? Or just 98? So 987x minus something, right? 1.22. Okay, so now we have this linear model. Repeat. So we need 1980, 2000, and 2012. Okay, so since the equation is tiny, I'm just going to type it into my calculator because I can do that fairly quickly, faster than entering into the graph and then zooming out and all that. So I get 17.67 for 70. Now to do, what's the next one? 2000, so that would be 90. To do 90, I'm just going to go back up and select the same exact equation. Scroll over to the 70 and change the 7 to a 9 and press enter, and I get 23.06. You have to go up and highlight the equation and press enter. That'll bring it down to your next line. Then you can scroll over and change the 90 to, what's this one? 102. So I need to make it 102. Press enter, and there's your 3 answers. So you can get that answer very easily as well. It's just a matter of knowing which one's going to be faster. In this case, just using the calculator was definitely faster. So we have 17.7, 23.1, and 26.3. Okay, discuss your results and compare them to the cubic model. What do you think? The cubic one is more feasible? Okay, so let's talk about the cubic one first. Compared to the linear model, is it better or worse? The answer is it's both. It's better within the data, and that's, I think, what you were saying. It's more logical because it's following those data points almost perfectly, like we saw. But the problem is when we go to extrapolate a far distance away from our data, this one definitely fails. Whereas this one, in 2012, 26.3, is still reasonably close to that 30. It's not taking off like this one is. So discuss your results and compare them to the cubic model. I like this one better for the extrapolation because I know that we're not going to take off and start eating, a couple 100 pounds of cheese by the time it gets to be 2020. That's ridiculous. I guess it could happen. We are Americans after all. But more likely, it's going to follow more along the lines of this. So within the data, I like this one a lot better. Outside of the data, I like this one a lot better. Okay? Now, that's another thing you can do is you can come up with a cubic model or a quadratic model or some other model that fits the data really, really well so that within the data you can talk about it using that model. But then outside the data, this one is the better option, so then you switch to the other model and use this one to come up with your answers. Okay? I believe that's it.